Good morning, everyone. I am Santam Sinha, lecturer of civil engineering in Dreams Polytechnic. Now, we started the structural design part 1 of fourth semester civil engineering. There is a topic, is an analysis of singly reinforcement. In this analysis of singly reinforcement, we have to find out what is the moment resisting capacity of the beam. And whatever if one I tell you, if I told you that whatever the load is act on the beam and what type of moment will be developed, to counteract this moment, whatever the moment will be developed to resist, we have to find out. This is the moment resisting capacity of the beam. Now, before going to this, we have to finalize and analysis of the what is the amount of steel provided, what is the amount of concrete provided, this what is the size of the beam, what is the depth, height, the whatever we read about, this is known as analysis of singly reinforced beam. So in the singly reinforced beam, one thing I want to convey, the reinforcing bar are embedded in the tension zone. But in case of doubly reinforced beam, there is both the tension zone and the compression zone. There is both reinforcement bar are provided. So we have to calculate the moment of resistance and what is the tensile force, what is the compressive force, what is the depth of neutral axis. The axis where there is no tensile force exist, there is no compressive force will be exist. We have to find out. So analysis singly reinforced beam. Okay. Analysis of singly reinforced. Try to understand. If there is a beam section, if I take here, this is a beam section. This is a beam section. And in this beam section, let us take this beam is rest. This beam is rest over a fixed. Let us take it is rest over a fixed. In this beam, we have to find out the moment resisting capacity. Okay, let us consider this total length of the beam is L. Okay, and let us consider there is a uniformly distributed load each act over the span of entire length. Okay, and these are the supports. And let us take, I have cut down a section here, X, X. Okay, this is the length of the beam, this is breadth of the beam, this is depth of the beam. Up to this is overall depth of the full beam. Up to this, there is a tension reinforcement bar are provided in the tension zone. That is my point. This is tension zone and this is neutral axis, NA. I did not know why, NA. In this axis, there is no tension and no compression will be exist. Above the neutral axis, if this is a beam, if I apply a load over this, then what is happening? It is a bend like. Then the lower portion is known as tension zone and the upper portion is known as your compression zone. Okay, this is compressive force developed and the tension force. If I cut down the section to draw here, it will be look like this way. It will be look like this way. Try to understand here. This is the section I have to draw here. In this section, I told you these are the tensile reinforcement bar are provided. Tensile reinforcement bar are provided. We can name it also area of steel. In tension zone, area of. Okay, so we have to know that this is the area of tensile reinforcement bar. So we can write down the AST, area of steel in tension zone. Okay, this is the neutral axis. Let us consider this is the neutral axis. Okay, this is the neutral axis. Okay, we have to draw the stress strain diagram of this beam. We have to draw the stress strain diagram. So that's why we have to know about the assumption regarding this stress strain diagram. What are the assumptions? The plane section remain plane before and after bending. Before bending it is plane. After bending it is also plane. Let us take the plane section here. If we consider the plane section, after bending, before bending, this section remains same. And if we draw the strain diagram, the maximum strain taken by the concrete is 0.0035 or 0.35%. Then if we end, third assumption is what? The strain diagram is linear, but the stress diagram is, first we have to draw the parabolic and rectangular in section. So if we draw the strain diagram, it will be look like. And we'll take up to the tension because steel is stronger in tension, weaker in compression. Due to this is a tension zone, this is compression zone, up to the steel we have to consider. And tensile stress in concrete is ignored. This is the one of the assumptions. So what is the maximum strength? 0.0035. I told you here 0.35% of strain will be taken. But after 0.002, it will be start falling. 0.2% of strain, 0.002. And this is the maximum strain. This is one of the assumptions taken by the maximum strain taken by the steel. This is steel, this is concrete. Maximum strain taken by the concrete here, maximum strain taken by the steel here. Is how much? 0 point strain in steel, you can write down here also. This is strain in concrete, you can write down also. Strain in steel is how much? 0.002 plus 0.87 Fy by yes. Fy by yes. Okay, you know what is this is the cube strength of concrete and steel. We have to draw at 0.67 Fy by yes. So same thing, if we draw the stress diagram, here, this is up to this, you can find out the tension force Tu. Let us take Tu. And the ultimate tension force, or simply says Q or T, whatever. Now this will be parabola. After that, it will give a rectangle, and this rectangle is denoted from this axis 0.00. Getting my point? Then whatever the force developed here, 0.446 FCK. One of the assumptions, you can find out the design strength. Of where is the concrete. Design stress of concrete is how much? 0.67 FCK divided by 1.5 is the partial safety factor. We can get 0.446 FCK. And you know, this is how to find out 0.67 FCK. This value will be found out by FCK divided by 1.5 is the partial safety factor of concrete, and we can get at 0.67 FCK. Okay, so we can find out at 0.446 FCK this way. Now, how to find out? This is the depth of neutral axis. First intention, we have to find out the depth of neutral axis. Don't have done knowledge about what is the value of x. Let us consider this value is how much? X1. Let us consider this value is x1. And this value is, let us take x2. Okay, now we have find out the x1 and x2. by using similar triangle OC, this is B, this is D, the triangle OCD and triangle OAB. Okay, OAB. In this two triangle, we can find out the value of XU divided by 0.0035 is equal to how much? X1 divided by 0.002. X1 divided by 0.002. If we solve this one, we can find out the value of X1 is how much? 4 by 7 of X. 4 by 7. This is 4 by 7 of X. Okay? And we have the idea about X1 plus X2. X1 plus X2 is equal to XU. X1 plus X2 is equal to XU. So X2 is how much? XU minus X1. So if we solve it, we can get the value of X2 equal to how much? 3 by 7 of X. This is 3 by 7 of X. 3 by 7 of X. So these two values. And by using these two values, we can find out the stresses here. Let us consider, we have the idea stress equal to force per unit area. So force equal to how much? Stress into area. So there is a compressive force will be acting in the rectangular section is how much? C1. This is how much? C2. And the distance from this to this, C1 is how much? Let us take Y1. And from C2 is how much? Y2. The average compressive force will be act here. This is known as letter C and at a distance of Y bar from the top fiber. Y bar from the top fiber. By using the center of gravity method, we can find out the average stress. This is the another force TU or known as also T. This is CU also known as T. This is the breadth of the section B. I already told you in the first drawing and first figure. This is the average overall depth D. This to this is the effective depth up to the center of the tensile reinforcement part. This is clear cover, up to this one is clear cover CC, and this to this is known as what? Effective cover DC or DE, effective cover. So we can find out the forces. What is the compressive force? What is the tensile force here? Compressive force. So to find compressive force C. C equal to we know C1 plus C2. This is average force. C1 plus C2 gives C, average compressive force. So in the first case, we find out to find C1. This is compressive force of the rectangular block section. So what is the compressive force? Compressive force, we have the value stress into area. So C1 equal to average stress into area. So what is the value of average stress here? Average stress is how much? 0.446 FCK. What is area? Area of the rectangle here? B into up to how much distance rectangle exists here? Is x2 distance. X2 is how much? 3 by 7. So B into 3 by 7 XU. So what is the value get here? If we calculate it, we can get the value of 0.19 FCK XU B. C1 value in this one. So to find C2, C2 is how much? Same thing. Average stress into area. Average stress into area. Used for the parabolic section. And you know the value of a parabola. This is major parabola. We draw. This is minor parabola. So area is how much? Let us take this is A, this is B, this is also A, this is B. Area is how much? 2/3 of AB. Area is how much here? 2/3 of AB. This area is how much? 1/3 of. So this parabola it looks like a major parabola. So what is the area here? Average stress in first average stress is how much? Something 0.446. What is the area here? 2/3 of AB. So 2/3, 2 by 3 AB. This is how much? B. Then what is the distance? A is how much? What is the distance here? X1. X1 is how much? 4 by 7. 4 by 7 of X. Then what is the value of C1? C2 is here. C2 is that we have to solve. We can get 0.17 FCK, XU. So total force of C is how much? C1 plus C2. So 0.19 FCK XUB plus 0.17 FCK XUB. So we can get the value is how much? 0.36 FCK XUB. We will get the value of Cu or simply C. C is how much? We can get here the value 0.36 FCK XUB. And T value? T value same thing. Stress equal to force per area and force equal to how much? Stress into area. This is the what is the stress developed here? Due to this tension steel, the stress is 0.87 F1. And you know this value, I have to find out 0.87 F1. We can find out this value by the design strength of steel FD equal to how much? Fy by 1.15. This value is partial safety factor of the steel. So Fy by 1.15 is getting how much? 0.87. So this is the value. 0.87 Fy is the average stress. And what is the area? Stress into area. Stress into area gets first. We can take average stress of steel is area of steel, AST. Area T, AST. If we compare from the neutral axis, compressive force equal to tensile force, we can get 0.36. Compressive value is how much? 0.36 FCK XUB is equal to how much tensile force? 0.87 Fy AST. So, what is the value of XU? Neutral depth of neutral axis. XU is depth of neutral axis. Is equal to how much? 0.87 Fy AST divided by 0.36 FCK into B. This is one of the assumptions we have to draw in depth of neutral axis. Depth of neutral axis in single length for spin. Some of the code book we can XU by D is equal to this one by into T. Nothing else. D is not called. Cancel out. But the major thing is moment of resistance we have to find out in the next class. Thank you.